Alright, time for another DraftPhysics.com, debatephysics.com, also video presentation. Yeah, so there's a channel called Idealized Science Institute, it's just pointed out. Dr. Wargo, probably a physics teacher. Alright, anyway, I don't know a lot about him. A couple of videos here. It's just, again, this is, don't want to be pointing fingers, but it's just really kind of sloppy science. And, this is why science can promote and propagandize things that just aren't true, is because they can make an experiment look like something when it ain't really showing the truth. So this is sort of back to Deschartelet and the whole kinetic energy thing of, denting clay with round objects, or rolling a ball on a surface and pretending you don't know that gravity is going to change. The amount of friction is going to change based on how fast something's moving. People are still doing that experiment, right? Despar, I think. I accidentally saw one of his videos. He's pushing a wooden block. It's the same. It's the same experiment. No point in redoing it. I've already conceded that, yeah, in friction, that if you roll something twice the velocity, it'll go 4 times the distance. But it's only because you're defeating. It's only 2 units of friction for the 2 units of velocity. Because it's only 2 units of time to go 4 times the distance. And so you're going through the gravity quickly, and it makes a difference. But anyway, all right. The amount of weight you're putting on the surface changes based on how fast you're going across the surface. Anyway, all right. So it's that kind of stuff, and it's just not good science. And but there's nothing personal in this. I'm just saying, come on. The only way this is ever going to change is one of these physicists has to say, yeah, we have to do better than this. We actually have to measure, 4 pounds dropped 1 foot and 1 pound dropped 4 feet, and actually prove that they're the same impact energy.
For today's quiz, we have a vernier force plate. We have the old vernier software connected to a very old computer. It still works. In fact,
So you're saying it still works, but none of this is very reliable. Okay, this whole idea of digitally measuring masses, impact weights, is kind of suspicious in the sense that the technology really isn't up to the task of measuring the whole substance of something's mass over a relevant period of time. It just isn't. It would be better to use a mechanical old style spring.
This version. This is not an app. This is where you would literally download the program onto the computer.
You have to download apps, but whatever. Okay, fine.
Regardless, our question today is if I have a basketball and a bag of sand.
So just analyzing the two things. Obviously one of them is just a spring. You could just argue the basketball is a spring. It's a different kind of spring. It's gonna deform in a different way than a spring, but the idea is exactly the same. It's going to deform, store energy in the deformation because it's going to be able to return to its original shape. So you're basically just dropping a spring on a spring. All right, what do you think is going to happen? Do you think the second spring, the bottom spring, is going to measure the actual weight of the object, or is it going to be likely that it's going to weigh half as much if the spring has absorbed half the energy? So if I stack springs on top of, if I put a scale on top of a scale and then drop a basketball on it, both scales are going to read half as much of the real weight. That's what you're really going to get. He gets exactly the opposite. So that's why I'm playing this video, is because that's the deception, is that obviously this technology is way under qualified for the experiment you're using it for. And the other argument is the bag of sand is again another deception, as if this bag of sand is going to give all of its energy to the scale, when the bag of sand means that the sand's going to move in all kinds of directions. It's not going to be going down. It's going to be going sideways and doing a lot of other stuff. Bouncing. It's going to do a lot of stuff. The little bits of sand are going to do lots of motion. And that motion is stealing the impact energy, just a fact. So you'd be better off just using something more solid, a hard ball of the same mass.
And I've used this scale to ensure that they're the same exact mass, which happens to be 574 grams. If we were to drop these onto the force plate, which would have a greater force?
So this is the trick question kind of bullshit. Instead of just let's analyze the two situations and figure out how they're going to apply their force and how you're going to measure the applied force. And obviously the problem with the basketball is it has a tiny impact point. Okay, it's going to deform, which is just going to be basically compressing the spring of the basketball, and that's going to absorb a substantial portion of the energy, half of its capacity to produce an impact pressure. So it's like doubling scales. It's like putting a scale on top of a scale. You can't get a right reading.
That's our question for today. And I'll hold up.
So this is kind of the lame part of the video. You should have figured out by now. I don't want to be. I mean, there's plenty of criticisms for the production values of my videos, so it's nothing personal here. But I mean, obviously, this is not very readable, and So, and I mean, who is the test for? It's like you could do if it was just for classroom use, you can just make the videos unlisted and have people go have the link. But obviously, they're public videos. You're making an argument about physics. Anyway, but this isn't very useful, frankly. You ought to just put the question in the description, or some other way of, or just read it. It's not that long a question,
Quiz.
But this is sort of lame. Just saying.
As always, mark out your answer as completely as you can, and then list how confident you are in your answer.
Why? Why do all that crap? Why don't you just explain the physics? Why does this always have to be some challenge thing where try to figure it out and do it all the wrong way? Like somehow doing it the wrong way will be good practice in how to do things the wrong way? I mean, it's, you're just explaining a truth. Why would I explain the truth by explaining all the ways you could get it wrong? When, no, the thing to do is just to explain the right answer and explain why it's the right answer. And quit doing all this, whatever, turning everything into this. Just say, okay, now let's just analyze the variables and see if we can figure out the answer by analyzing all the variables. So you have the wind resistance, the air resistance. You have different things that are going to change how fast, obviously, the basketball is even going to fall. We know the basketball is not going to fall at the same speed as the bag of sand because air resistance is a real thing in this case. Huge surface area versus small surface area. So a huge bias. And again, the irony is his results are exactly the opposite. So even though the basketball has all of the cheats to its advantage, somehow it's going to weigh more, which, again, is just giving a completely wrong impression.
The response that we hear from students over and over is the bag of sand will clearly have a greater force than a bouncing basketball. And they feel that because
So they feel that. No, it doesn't have anything to do with feeling that. Okay, it's first they could understand that the basketball is going to do this deformation thing, and it's going to act like a spring. And I can figure out that if I put a scale on top of a scale, that both scales are going to read half the actual weight. And so the bottom scale can't possibly read the basketball's true impact because it's the bottom scale and it's only getting half the pressure. So they could actually figure it out. Okay, why? It's not just some, I think. Then they could just make the argument, well, the basketball is going to bounce pretty high off the scale. So obviously if it's bouncing off the scale, its energy couldn't be going that way because its energy is going that way. It's bouncing. There's energy in the universe. The ball's coming back. If I throw something in a brick wall, the brick wall doesn't take the energy. The ball comes back. They could do that logic. If it's reflecting, how can it also do work in both directions? It can't do work in both directions.
I've heard these expressions like, oh, you hit the ground like a bag of wet cement or a bag of sand or something like that. And a basketball will often say, look, it's light and it's going to bounce back up. And
It's light, so again, we know it's not lighter, okay, but we do know that it has a gigantic surface area and it's full of air. So yes, there is a buoyancy issue. It's really more buoyant in atmosphere than the bag of sand. It will travel slower than the bag of sand. If you threw both the objects, the bag of sand will go further.
literally just kind of float up into the air. So that's the most typical response that we get. However, some students will say, well, if you're dropping these from the same height and they have the same exact mass, the force should be the same.
Well, obviously it can't be in atmosphere. So again, that might be true in a vacuum, but it's not going to be true in atmosphere.
And those are the two responses that we get over and over.
So this isn't really in-depth analysis. It's really superficial, trivial, and frankly wrong.
I want to talk a little bit about how we're going to analyze this. The vernier system is going to end up using this force plate. Now it's a black box to us. I didn't create this, I didn't make the electronics, so I don't know exactly how it's working. That's going to be a problem anytime you have experimental.
Right, so what's the point? So if you have zero, you can't qualify it by showing how it actually does impacts. Yes, it might be fine as a scale for measuring weights, but it might not have any value as an impact detector.
I'm going. In this case, when the ball is hitting onto the force plate, we must ensure that that force plate is going to record the maximum force. And you might think, well, that's what it's designed for, but not so fast. Whenever I hooked up this sensor into the vernier system, there is a digital and then there is an analog channel. This went into the analog channel. That does not mean it's continuous though. And I'm going to show you this. I'm going to drop this basketball several times onto this force.
So I don't know what all this, yeah, it does the experiment all, so maybe some, well, I won't cut it out, but yes, the video does have all this bit in it that's just of no value.
Plate. And we'll set the vernier system to collect, we'll say 10 times a second. And that sounds like a lot, but you're going to see a major problem here. And I might as well explain it first. When this is hitting into the plate, it's going to happen, very quickly. If we sample right before or right after when it has its maximum impact, we can miss it altogether. And I'll show you how inconsistent this is. If we set our sample ratio or sample rate too low, then I'll increase it. Give me a second.
Yes, but the point is if you took it over a whole second, you'd be fine. And it'd be, the more divisions in that second is fine, but that's not the problem you're having. The problem is that the event does happen within 1 second, so you should be able to capture all of it within 1 second. And just the fact is it's not adding up all of the force correctly. It's not working.
I've set the program so it's going to...
And the other thing is the plate isn't even mounted to the table, so the plate itself is going to bounce, which can't help this experiment at all.
Record 10 samples per second. I already have the little arrow on.
So this again is, I'm just pointing out production-wise, it means absolutely nothing to point out stuff in a video that can't really be seen at normal, let's say average resolution, is not going to produce, not everybody's using high definition, not everybody's watching it on a gigantic monitor. They're not going to be able to read any of this, so no real point.
Collect, so hopefully I can just hit this button and I'll drop this several times in a row to show you the variability that we get.
So this is a little annoying, so I'll turn the volume down when it gets to this dropping thing. Here it is. Even more. So you can see the plates bouncing up and down, which really can't help the experiment at all.
You can see on this graph that we missed the hit most.
No, I can't see anything on the graph, so yes, absolutely useless. Sorry, no sale.
Most of the time. Only one of those bounces hit.
So only one got recorded as some sort of jiggly line.
I've now set the data collection to 500 samples per second. Before, when it was hitting, I might have been sampling before.
There's so much you can do with this subject in terms of just talking about the fact that as you lift a basketball and drop it, its weight changes, right? So if you just let it sit on the scale, it has a weight. The force indicator should be able to say how much force is the basketball applying to the scale, the detector, whatever it is. And you drop it from 1 centimeter, theoretically that doubles its weight. Okay, that's what I found anyway. And 4 centimeters double it again, and 16 centimeters doubles it again. And so by the time you're going 1 meter, you're talking about something, weighing 100 times more or 500 times more than it did.
Before or after the hit. Hopefully at 500 samples per second.
I mean, that to me is really the important part of this physics, is understanding how much of an effect that velocity is having on the impact weight. And the simple argument I make is that, yes, twice the velocity, twice the force, 3 times the velocity, 3 times the force, 4 times the velocity, 4 times the force, as Newton stated. And essentially disproving any notion that this kinetic energy stuff, 1/2 mv squared, has anything to do with reality.
We'll be able to get the maximum hit. And you might ask yourself, why not always leaving it at 500? Well, it bogs down the vernier system and the computer. It might not even display in real time. It'll show up afterwards.
Right, so again, you just wonder if this is having such a technical problem reading something so simple as the impact pressure. And again, the spring can do that. A spring can measure impact.
As you can see, we captured most of the hits.
Yeah, I
and
can't see it.
They're fairly consistent.
Can't see even what they say, can't see anything. So yes, thank you for... So what number did they read? What weight did the basketball have? What amount of force was it placing on the plate?
Now we're ready to actually drop our bag of sand and compare that with our basketball. I have a new run ready. All we need to do is hit collect. I'll drop the basketball 5 times, and I'll try to drop the bag of sand 5 times. I have a little bar to let me know that I'm always dropping from the same height each time.
So again, I just put this in the category of a Deschartelet experiment. It's just, this is really, it's not good science, to do experiments sloppy and without any real hope of your answer being reliable or precise. So the plate bounces less with the sand, that's for certain. Okay, so at least we can establish that. But obviously, again, why the bag of sand?
You can see that I have 1, 2, 3, 4, 5 of my basketball hits and only 1 of the sand. I'm going to redo this and make sure that this is not a fluke with the sand. But right away you can see the sand is going to have much less force.
So you heard the statement, the sand has less force. Even though the physics says there's no way that can be true. Okay, that the sand actually applied less force to the plate. Because even though the sand is moving, it's not another spring. It's not obviously taking half the energy out of the system. All right, we don't really need to see the. Okay, I'll just do it again.
And you can see again that the bag of sand delivers much less force, roughly half the force of that basketball.
Right. So, but we don't have the numbers, and there's a way to what the absolute would be if these were both perfect substances, in terms of they hit the scale without deforming or spreading. So the sand deforms and spreads without any elastic capacity. That is, it can't give any of that energy back. Where the basketball deforms and it, to some extent, will push at least half the energy back in one direction, and the rest of the bounce, again, is energy that didn't go into the scale. But it's just totally deceptive. And the real question is a reflection, is there any truth to any kind of notion that you can put energy into something and get a reflection? That somehow it's okay. You start with 100 momentum and you could put 100 into this object and you could have 100 reflect. Or even worse, you could hit something, give it 200 momentums, and then still get 100 back. Is that real? Does that really happen in this physical universe? If I did that experiment in space, is that my expectation that I can use up 100, I can use up the energy to create 100 momentum in an object, and I can manifest in the universe 300 units of motion? Would Newton say that can happen? More important question, I think. So let's see if he brings up air resistance. Okay. Let's see if he brings up deformation, elastic deformation of the basketball. It's a spring, essentially. Or if he brings up anything about the fact that the sand spreads as it hits the surface.
I've zoomed in and auto-scaled my data. While
Still can't see any of it.
it's not perfect, you could see I have 3 hits from the bag of sand. It's still not perfect. You could see that there's a little bit of variation there. I would like to crank it up to 1,000 samples per second, but that's really the limit of what this vernier system can do. It has a hard time and sometimes locks up. But if you replicate this over and over, the general trend that you find is the basketball delivers much more force than the bag of sand. Why is this? Well, first of all, when the bag of sand is dropping and the masses are the same, so that's not a variable.
Well, we know it is a variable because the air resistance between the two would be radically different, and the basketball will, in fact, like a feather, it will drop slower. Its velocity will be lower.
They're both being dropped at the same height, from the same height, and they should end up hitting at the same velocity.
So they shouldn't. We know. I mean, I don't know how big a difference it is at a meter, but there is going to be a difference.
But that's where everything is going to change. We know that impulse is equal to the change in momentum. So if we think of the change in momentum,
again, it's the momentum. It isn't, this idea of the change in momentum. You're measuring it on a scale. I mean, you're just measuring how much force did it collect, is the idea. And you're saying, can you collect all the force with 2 objects that deform? So obviously they're hitting the scale and they're deforming. That's right there is telling you, oh, well, if the shape of the object changes, that takes energy to change its shape. So the shape change will steal some of the energy. And the question is how much of the energy does it steal?
when the bag of sand goes from a velocity to 0, it has a change in velocity, which is going to be proportional to the force. Not exactly, we have to get time in there, but in general, force is proportional to your change in momentum.
Yeah, that's Newton. So, and the real point is which way are the forces going? So obviously, again, where does the energy end up? And the point is that the bag of sand, you're obviously create a lot of heat in the sand because it's banging into each other. Lots of places where you're losing some of the energy because of the chaos created in the sand. And with the basketball, the same thing's happening. You're heating the rubber, okay, so that's not going to get that energy back. I mean, there's lots of places where you could point out that you can't measure it this way because these two objects are changing. There's too many variables affecting how they put the energy, keep the energy going in one direction. The energy doesn't stay going in one direction. That's the problem. You can't measure if it's not going in the same direction.
Let's say this is coming down at a -1 and then goes to 0.
So this is more of this nonsense that we're, going to play plus and minus games with its momentum. Like there's something like a minus momentum. No such thing.
You have a difference of 1, where the basketball, when it comes down and it's going to change its velocity to 0, that would also be a change in velocity of -1.
So it's really not. Just like a spring, it's going to start compressing before it finishes. So it's going to start applying pressure to the other spring, the scale, before it's completely compressed. So the spring starts absorbing the energy. It starts pushing in both directions. It starts applying energy to the scale. And as it compresses, there'll be a point where it now compresses the spring all the way. It's still moving in this direction because it's gave it momentum. It's already given this object motion, the scale, the bottom scale. And the fact is now it's going to expand, give this a little bit more, and it's going to create a reflection. But the reflection can't be, okay? It's still energy moving in a direction, and it doesn't matter which direction energy is moving. And that's the key point that physics has way wrong. There's no such thing as a minus directional motion. It's all energy. Any motion in any direction is energy. Any motion in any direction is energy. You can't put a certain amount of energy in and get motion out that's more motion than you started with, mass and velocity. You can only conserve the momentum.
However, it is bouncing back up. So if it goes from -1...
All right, back. Bit of a allergy thingy.
to 0 back to +1. -1 to 0 to +1 is nearly twice the difference in the change in velocity as the sand.
So it really wouldn't happen that way. And again, if you did it with scales, 2 springs and then drop something, you'd understand there's no way the bottom scale could read the full weight of the object. Can't happen. So 2 springs, okay, in series, the bottom spring will not register the full mass. So, it doesn't make any sense that he's arguing that that's what's really happening, that somehow the basketball actually did impart twice the force. It's just this experiment is a piece of garbage. All right, that's why it came out this way, and that's the only reason. And again, you have to explain why the bag of sand loses so much more energy. And that's sort of explainable in the sense that, yes, it deforms a lot. The sand particles don't keep moving in one direction. They move in all kinds of other directions, which means they're going to lose their impact energy by moving in a direction that isn't into the scale. All right.
So the object that bounces in this case is going to have much more force.
So it's just wrong. The more it bounces, the less force it's going to deliver to the surface. You're better off getting hit by a rubber ball that can bounce off of you than you are getting hit by a baseball or something that doesn't bounce. Just a fact. Real physics.
Than the object that just splats. That's your quiz for today.
It's wrong. It's bad science. Sorry. It is. And so somebody, again, this isn't going to change until physics wakes up and says, yeah, we have to have some credibility. We can't claim stuff to be true, all right, that isn't true. It's just, that's not fair to your little child minds that you're perverting with these wrong statements about the reality. All right, so let's play another video of his. And I need to pause to do that. All right, so in this video, he's just going to do the gun thing. And, instead of talking about the fact that physics says that Newton's laws don't have anything to do with this device, that the recoil is going to have 2 joules of energy, the bullet's going to have 2,000 joules. There's not going to be anything like an equal and opposite reaction in terms of the distribution of kinetic energy. And the fact is that kinetic energy doesn't exist. The only thing is matters is the momentum. The bullet has momentum, and you could show that momentum will change based on how you do this experiment. And so if you would have just done the experiment, one with the gun can recoil, and the other experiment where the gun can't, where it's locked to the surface, then you could logically understand the rubber band, the mechanism producing the force, is now not going to be doing this extra bit of work of moving the hunk of wood. And the only place that extra work can go is into the projectile. So now the projectile will go further because you haven't wasted energy recoiling the piece of wood. So again, it's just really incomplete science. This isn't a good argument. It's not the truth. What he's claiming the effects to be isn't accurate. And again, he doesn't even go into the obvious conflict with Newton's laws here, where the kinetic energy says one thing and the momentum says something entirely, crazy difference in the two statements about the reality. That all you've changed is the form of the force. You put it in a little tiny thing going fast versus, one atom going 1,000 miles an hour versus 1,000 atoms going 1 mile an hour. And to claim that these two things can move more matter is like the 8-pound bowling ball going 16 miles an hour versus the 16-pound ball going 8. Diagram it. Go diagram how the 8-pound ball does twice the work, because it can't. Because the only thing it can give the pins is its momentum. It can't give the pins momentum it doesn't have. It can just give it momentum. So obviously they can only move the same mass, the same amount of velocity, the same total MV is all they can do to those pins. The kinetic energy is irrelevant. It's meaningless. It can't do any work ever because it's not real. That's what he should be teaching.
Today's quiz involves a projectile launcher. It's made using a piece of PVC. I have a piece of dowel rod that has a bolt at the end. You can use rubber bands to propel the projectile by putting it from a screw up here down to the bolt. If I load it, I can put a trigger through the PVC into the plunger. I could then take the projectile and slide it down into where it hits the dowel. It is ready to be fired. Our question today, though, is if I took the projectile out of the projectile launcher and then pulled the trigger, what will happen? Now, there's one caveat to this. I have put ball-bearing wheels on the apparatus, so it moves readily with very little resistance. So here's what your quiz looks like today.
So I don't know if it matters how slick you make it. Obviously, you don't need great ball bearings to get the basic theme. So again, you can't read the quiz, really a point. So again, this is sort of a simple argument that everybody sort of knows, okay, you're moving something internally. You can't gain any velocity. You have to throw something. And the only thing you'll be throwing is a tiny bit of air. So that's all you got. There's nothing because you've removed the projectile. So you can't go anywhere if you don't throw anything. Just waving your arms won't move you in space because you're not throwing anything. You have to throw something. Again, it's all about momentum. And the truth is, though, this illustrates how meaningless kinetic energy is because there's no kinetic energy portion to this. It won't matter what the kinetic energy of the motions are. So even though the bolt is going to be moving with a kinetic energy higher than the recoiling wood, it wouldn't make any difference because it's only about the momentum. Only.
As always, mark out your answer and list your level of confidence.
Why would I do all any of that? It was just, why? I mean, why do this testing before you've really explained or gone through all the variables? So again, it's really important just to isolate all the variables.
Typical student responses include three. First of all, they see the rubber bands, and when I pull the trigger, the rubber bands are going to pull the bolt forward, causing the entire apparatus to move forward.
Well, that would only happen if the bolt had a tremendous amount of drag on the apparatus somehow, but even that still wouldn't work because rubber bands are still pushing the other way, right? So you're not going to go anywhere.
The second most likely scenario in the student's mind is, well, I have been hunting before, and I know when I pull a trigger on a rifle or a shotgun or something like that, it wants to kick back. Others will say, yeah, but there's no projectile here, so nothing's going to happen.
Right, so the trick is with a gun, okay, so even if there's no bullet in the gun, you're still shooting an awful lot of chemistry and air and whatnot out of the gun, so you're still going to get a significant recoil.
So those are the three most typical responses.
I mean, shooting blanks still has a recoil.
To help explain what's going on here, let's use a more classic case where we have the projectile loaded into the apparatus.
Right, so this is the experiment I wish you would have done. So do the experiment without the wheels, or just hold the device, lock it down in some way so it can't recoil. And then shoot your projectile. And then do it with the wheels. And my argument's going to be is the projectile goes further when you don't have someplace else to put the energy. When the energy can't get into the piece of wood, it has to go the one way. It can't go both ways anymore. So even though it's putting pressure on the wood and saying the wood wants to move, the wood's not accepting the pressure, and it's just reflecting it. So all the energy would have to go in the direction of the projectile, at least more of the energy. We know that the lighter the object you're pushing, the less and less efficient the spring gets, but regardless.
According to the conservation of momentum, which as far as we know has never been violated.
Right, so what's the point of talking about kinetic energy when as far as we know it's always violated? It never does any work, ever. I mean, unless I'm transferring energy from one mass that's exactly the same as the other mass I'm transferring it to, in every other case, kinetic energy whacks the whole experiment. You never have conservation. You never start with this much kinetic energy and end up with the same amount of kinetic energy on the other side.
If we start off with zero momentum, we should end up with zero momentum.
So again, it's just more nonsense about talking about zero momentum when you have objects flying in different directions. It's just idiotic. It's such a bad physics notion that somehow there is this idea that motion in the universe, this going this way is negative, going that way is positive. No, going that way is positive. What's the point of that nonsense? Motion is always energy. Any motion, any mass moving is counted as energy. There's no such thing as this is intrinsically unenergy or intrinsically anti-energy. Everything moving is energy.
So if the projectile is going forward, well, the apparatus should end up going in the opposite direction. Let's try this out. It might be a little bit loud.
Right. So like I said, unfortunately, the simple experiment is do that with a brick, a cinder block behind the wood so it can't move. All right, and do it without the cinder block. And my argument is you'll see the obvious difference is that now you're not moving a bunch of wood. All right, you're not moving a mass in this direction. You're not wasting energy going in the direction you don't want to see something happen in, the projectile direction. So if you can lock the gun down and stop the recoil, you can add a little more energy to the projectile. Now in a gun, it's not going to work because the explosion is so fast that reflections aren't really going to be relevant. The bullet's already gone before any energy can reflect and hit it. But in this case, it certainly will make a difference.
And you could see the apparatus goes backwards.
Right, wasting energy. Okay, that's energy that didn't go into the projectile. That's the simple argument. That's energy didn't go into the projectile.
Let's now load this without a projectile. In this case, when I pull this up on the trigger, it's going to allow the rubber band to come forward. So you might think we're going to end up going forward. But remember, in order to load this, I literally had to separate these two. One going in a positive direction, one going in a negative direction.
So there was no positive and negative directions, and the expansion of the rubber bands, the rubber bands couldn't care less. They weren't saying, oh, I'm stretching more to the left than I am the right. They weren't playing any such game.
I pull the trigger, I have 0 total momentum before. Yes, it's true, the plunger is going to come forward, but it's also going to be pulling with an equal and opposite force through these rubber bands, pulling the apparatus back. So in other words, they can't.
So unfortunately, it does happen so fast that you can't do any frame by frame, but the fact is it does move a little bit backwards and then stops. And part of that might just be because you are moving air out of the gun.
To each other, and we would expect to see no effect at all.
So it does go back a little. So it's not like there's no effect.
And that's your quiz for today.
All right. So, and again, it's just not good science. This is why science goes foul, is because it won't do these elemental, fundamental experiments honestly and correctly, and instead just does this show stuff where they can get away with saying something that just isn't true. Now, no, nothing he said here was untrue, but I'm just saying, obviously he left a lot off the table. The whole discussion about the fact that the projectile says it's got a huge amount of energy, and the recoil is a tiny percentage of that energy. So the stuff going this way is a tiny amount of kinetic energy versus this gigantic amount going the other way. And there's no hope of that being consistent with any notion of a third law. So just accept that you can't have it both ways. You can't say Newton's third law is relevant and meaningful and then say kinetic energy is real and that it can do work. Because the fact is it can't. Again, I'll just go back to the bowling ball. We go back to the 5 mass going 10 velocity going this way and a 10 mass going 5 velocity this way, and if you simply let them do a tug of war, have a string uncoil, and they stop, they measure each other's weight, each other's capacity to produce force or pressure, they clearly will not. The 5 mass will not show that it has twice the energy. It won't win. And the same is true of a 16-pound bowling ball going 8 miles an hour going one way and an 8-pound going the other way. And we make a metal brace and both bowling balls hit the surface at the same time. The brace isn't going somewhere. One of them isn't going to win. Because the fact is they have the same frickin' energy. They have the same capacity to do work. And those simple experiments will prove the point, and in 350 years since Newton, they won't do those simple experiments. They won't detail and qualify their axioms of the truth. They won't show us the evidence. They won't crash a car. They won't do anything to show that it takes 25 times the fuel to move something 5 times as fast. They won't show us that experiment because it doesn't happen. It's not good physics. It's a crappy axiom. It's a piece of nonsense. There is no 1/2 mv squared in the physical world. It's only a delusion in the minds of bad scientists. Because it's obvious that it's not true. The lever proves it. The ballistic pendulum proves it. Rolling proves it. And, dropping things proves it. Okay, 4 times the distance, only twice the time in the gravity. It's a force, 9.8 meters per second, 1 second. You get 9.8 meters per 1 second. That's the fact. The fact is 4 times the distance only falls 2 seconds. Twice the time. It only has twice the force. It only collected twice the force because it was only in the force twice as long. I mean, it's obvious that this is junk science. And here, you can't get a single one of these people to show the integrity to say, yeah, those are a lot of good arguments and we really should fix this. And quit doing these gimmicky experiments that are essentially rigged to propagandize a truth, not to show a truth. All right. No, probably enough. Yeah. Okay. So, till the next time and such and so forth and whatnot. Like I say, no hard feelings. I'll post, let's see if this guy will interact. Because again, it's not going to change until these people change it. They have to change it from the inside. It can't be changed from the outside. People out here can't change their religion. Okay, they have to have one of their bishops has to turn. One of their authority, the Pope, has to turn. And until that happens, nothing's going to improve. They're not going to ever fix all of these errors they've made in these fundamental axioms. Just a fact. And it shouldn't be a fact because these are smart people and they should have the integrity to admit, yeah, this physics isn't really tight. As much as we claim it's the most proven theory in history, it's really not proven. It's really not demonstrated by decisive evidence. It's demonstrated by, smoke and mirror experiments, not the real thing. All right, enough said.